Hello my dear students, welcome back to NEET WORLD. So we will be discussing chemical kinetics. So this is our second session on this chemical kinetics. I hope you have watched the previous session on this chapter where I have covered zero order reaction, first order reaction with some numericals and PYQs related to these particular topics from EAPCET exam. Okay, I hope you have watched it. So if you haven't seen that, just after completing this session you can watch it. Okay, right, that will be very useful for your preparation. Okay, let's make it complete the second or the remaining part of this particular topic here. Okay, so these are all the questions that I have collected from this EAPCET and I have solved in the previous discussion. See, look at these questions. This one, this is a zero order reaction. Yes, we have did this, and this is a for I can say rate expression you can write. We need to write a rate expression. From that we need to express what is the rate of this particular reaction out of this 4. Okay, and the next, so how can you give this for a first order reaction? How can you calculate rate? This is also discussed in the last session. Yes, so I am just showing that if you are clear with these questions, are you able to answer this? It's no issues. If not, you can just watch my previous session on this particular discussion. Okay, right. And look at this, what they are saying, for a first order reaction A to B, for a first order reaction A to P, the following graph is obtained. The rate constant and the initial concentration of A respectively are given. Y axis is ln of A minus x and x axis is time in second. Okay, this is ln of A minus x and here it is in time in seconds. That's it. Very simple. See, what is the equation we can get for this? We have ln like this for first order reaction, we have T equals to 1 by K ln A by A minus x we have right now. So from this you can say Tk which will be equals to ln of A minus ln of A minus x. Okay, so they are drawing this graph ln A minus x versus t, that is time. So it means you bring this here, so you can write this as ln A minus x is equals to ln of A minus T1k. Okay, that's it. So Tk1, that's it. Okay, so from here you can write this as y is equals to mx plus c graphs you will get, that is minus t is a slope with k as a constant plus ln of A. Okay, this is ln A minus x. Okay, so you got y equals to mx plus a c type graph. Okay, so where m is a negative slope we have and intercept with positive, therefore you will get a graph like this. Okay, so now this is in form of ln right now, so they have mentioned it as ln, that is also fine. Okay, so now what is the slope they have mentioned? Minus 10 power minus 2, that is nothing but minus t is equals to minus 10 power minus 2, so time is equals to 10 power minus 2. Okay, so that's it. So this not time, here k is equals to 10 power minus 2. Okay, 10 power minus 2 given. Okay, so where do we have 10 power minus 2? Yes, here and see respectively time in seconds. So what they are asking, the rate constant and initial concentration. Rate constant is how much? 10 power minus 2 here. Yes, these are the two options we have. And the next, what about initial concentration? This ln of A is how much they are saying. See that ln of A here we have 2.303. Yes, where do we have 2.303? Yes, here we have 2.303. Okay, that's it. So first this option B will be a perfect answer for this particular question. Yes, if this is clear, just mention that is clear in the chat box. And look at this question also discussed in the last class. Here I will again give you some hint how to solve this question. See here, concentration of A increased 2 times and concentration of B is remained same, whereas the rate is also increased 2 times. Therefore order with respect to this particular reactant will be 1. Okay, so order with respect to A will be 1, and similarly you can see this data from 2 to 3 concentration of A is remains constant, but here it is increased 2 times, where rate is also increased 2 times. Therefore, order with respect to B also 1. So you can write rate equals to K concentration of A2 into concentration of B2. That's it. This is the equation you can get. They are asking the following data is given. Consider the gaseous reaction. What are their orders? What are their orders we got? Orders of reactant A is 1, orders of B is also 1. Okay, and total order of this particular reaction will be 2. What is the total order of this reaction? 2. 1 plus 1 is 2. And now in the same question, what if they ask this rate constant? Very simple. Substitute any of this data in the given in this particular equation, you will get this K value. So try to do this once. So let us take this first data, because it is relatively easy to calculate. So you can take 2.5 into 10 power minus 4 is the rate. I want rate constant K, where A concentration is given as 0.1 to the power 1 and B2 concentration is also 0.1 to the power 1. Okay, so this is 10 power minus 2. Here also 10 power minus 4 is there. You can just write as 10 power minus 2. That's it. K you got it as 2.5 into 10 power minus 2. So this is the value of rate constant for this particular reaction. Hope you got this clearly, I hope. Right now, let me show you one question and you just answer me in the same manner for this particular question. Okay, if you are facing difficulty to answer this, yes, you can watch my previous live session on this discussion of chemical kinetics. Very easy, and you know this is one of the very important model question for your NEET exam also. Okay, right, NEET and JEE also you can expect. Next, let me give you few more things here. Yeah, look at these. This is a question based on reaction mechanism. See, we know there are two types of chemical reaction. Again, this is very important model for your exam point of view. See, we know there are two types of reactions: elementary reactions, complex reactions. Elementary reactions means reactions takes place in single step, whereas complex reactions means it will be takes place in multiple steps. Either 2 or more than 2 steps will be seen. Okay, and during that complex reaction there will be something called intermediate will be formed. Okay, so look at this. These are the reactant molecules involved. They are asking a possible mechanism for this gaseous reaction given with 3 steps. The rate law for this particular reaction they are asking. See, it feels little lengthy but very easy to calculate. See, very simple it is. First of all, whenever you are writing rate law, that should be written for reactant molecules only. Okay, you need to have only reactant molecules in your rate law. Okay, but you know this reaction is taking place in this many steps, but you need to write for a complex reaction, you need to write rate law from the slowest step, that is rate determining step. So from this, if you write the rate law, R is equals to, what are the reactants here we have? I mean these two things, one is H2 and the other one is N2O2. So constant K multiplied with N2O2 with concentration of H2 we have to write like this. But you know this N2O2 is not our reactant, only H2 is our reactant as for the given reaction. So we need to remove this intermediate N2O2 and we need to write in the form of NO. So where do we how can we change this? Very simple. Look at step 1 mechanism here. So step 1, if you observe, in this step 1 you can write equilibrium reaction. K equilibrium is equals to concentration of N2O2 by concentration of NO. What is its stoichiometric coefficient here? 2 na, so write it as 2 power 2 for that particular NO. Okay, I do not want this N2O2 in the equation, so that I can make concentration of N2O2 is equals to K equilibrium multiplied with NO to the power 2. Okay, like this we can write. Okay, so wherever we have N2O2, replace that with this particular thing. So rate will be now equals to K multiplied with K equilibrium multiplied with NO concentration to the power 2 and H2. That's it. We are done with the question. That's it. How simple it is. Okay, and it is an important model question again. So now they will ask what will be the order with respect to NO. What will be the order with respect to NO? It is 2. And what will be the order with respect to H2? It is 1. So total order of this reaction is 3. Okay, that's it. So option 4 will be perfect answer for this particular question. Hope this discussion is clear without having without having any confusion here. Okay, and one more model I will tell you here. See, there will be like this: A plus B, or A giving rise to some B, again B will give some product C, and this B can again give back our A. Okay, this kind of the reaction they will say, and they will ask us what will be the equation for formation of C. So that is rate of formation of C, that is dC by dt for this particular equation, by mentioning this forward reaction as K1, and this is something like K2, this is like K minus 1 or K3, something like this. They will mention 3 constant. They will ask what is the rate of formation of C, that is nothing but dC by dt they will ask. How do we write these? Very simple. See, if we want to write the rate of formation of C, we know rate will be now depends upon rate of formation of C depends upon K2 concentration of B, right now K2 concentration of B, that is nothing but dC by dt if I want to write, plus dC by dt if I want to write. That is what the question here asking right now. They will give 4 options and we need to choose out of that one option. So just look at here, you will get complete clarity on this topic once you follow this clearly. See, whenever they say rate of formation of something, you need to write its constant K2 multiplied with its reactant. I mean, for this particular product this will be the reactant. But you know, this is not our exact reactant, this is our intermediate during the reaction right now. So whenever we are writing a rate law, intermediate should not be intermediate should not be indicated. It should be indicated in terms of starting material, that is reactants only, but not this intermediates, because intermediates are short-lived species. They will form to some point of time and they will disappear. Okay, so rate of formation of this intermediate will be equals to rate of deformation of that intermediate. Okay, therefore net change in the concentration of that particular intermediate will be 0. So it means what I am saying here, I need to eliminate this B from here, I should write in terms of A there. Okay, it's very simple, look at here. So rate of formation or deformation of B can be written as dB by dt is equals to, so it is forming from A right now, so you can write K1 concentration of A minus it is deforming from B to C now, so K2 concentration of B, again here also it is deforming like going back, so minus K3 concentration of B, like this we need to write. See what I told you, if there is any intermediate involved, its change in concentration will be 0, so you can make it is equals to 0. So from this K1A is equals to K2 plus K3 into concentration of B. Okay, we need to write it like this. So in the place of B I can replace, in the place of B I can write K1 by K2 plus K3 into concentration of A. Okay, this is what we can write in the place of concentration of B in this equation, so that I will get rate is equals to K2 into K1 by K2 plus K1, K2 plus K3 into concentration of A. That's it. This is our overall order of this particular reaction. Rate of formation of C should be indicated in this manner. Okay, I hope it is clear. Now what is the order with respect to A? It will be 1 and its rate constant will be given like this: K2, K1 by K2 plus K3. This is the rate constant of that particular reaction or particular rate of formation, you can say. Okay, hope everything is here we discussed is clear. Yes, hi in the chat box. Yeah. Next, can you tell me what is the rate of formation of this particular reaction? How can you write it? In the same manner, you just tell me your answer in the chat box. A plus B is giving rise to some C, which is an intermediate forming D here. Okay, here I am writing K1, here it is K2 and this is K3. I am asking you to mention what is rate of formation of D equation we will get. Okay, so how do you write this? Just try with the same step that we have did in the previous example, and let me know your answer in the chat box for this particular thing. Okay, right. This question we already solved. Next thing is this model again. In the last session I have discussed about first order reactions right now. So first order reactions, we can have, these are the important formulas you can remember for first order. Rate is equals to K concentration of A. So for this you can write a graph, draw a graph rate versus concentration simply in this manner. Okay, this is the rate constant slope one. Again second formula here you will get as like this. Minus dA by dt if A is a reactant forming some product. So you can write minus dA by dt equals to K1 concentration of A. Okay, and what is the integral equation we will get for these? We will get as K1 is equals to K1T is equals to ln of A naught by A we will get, A naught by AT we will get. Okay, so this is the concentration of A at time t and concentration of A at beginning. Okay, so from these you can write this as e power K1T which is equals to AT into A naught T, that's it. This is what you can make one more equation. Okay, so here you will get an exponential graph, T versus concentration of A at time t will be a exponential graph you will get. Okay, okay, and the next thing is here, this same equation I can write in other format like this. K1T is equals to 2.303 by log A by A minus x also we can write. Okay, and this one you can get one more graph from this as ln of A minus x into t in this format. So what is the slope here we will get? Slope is nothing but K1 and this intercept is our ln of A you will get or log A you will get. Okay, right. Okay, these are the different model graphs you need to remember from first order. Okay, and along with this we need to discuss about T half. T half of a first order reaction they will ask. See, from this formula T is equals to 1 by K log A by A minus x. It means the time required for completion of half of the reaction. It means concentration of reactant is now converted from 100% to 50, that is A becoming A by 2, that is becoming 50. It means simply you can take this A minus x as A by 2. So write T50 will be now written as 2.303 by K log A by 2. That means you can write here 2. So this becomes removed. So you will get T half is equals to 0.693 by K. So T half of the first order reaction is independent of initial concentration of a reactant. Okay, this is the formula we will get. Okay, and I have solved some questions related to this T half also. Okay, so let me show you one question. See, initially I have 100% concentration. Now it is converting into 50. Okay, like that if they give, so what is how many T halves here? It is 1 T half. Okay, for this 1 T half I am mentioning its time required for this process is 10 minutes. Okay, now tell me how many minutes of time required for conversion or completion of reaction till it reaches 75%, T75% I want. See, T75% I am asking now, what you will need to make here, after from 100 to 50 it is 10 minutes, from 50 to 25 again how many minutes you calculate. See, this is again a T half now. So from here to here I can say this is T75% or T3 by 4, 3 by 4. So this is nothing but this is 1 T half, this is second T half. So therefore 3 T by 4 will be equals to 2 T halves you can write. So 1 T half is 10 minutes, means 2 T halves means 20 minutes. Okay, like this they will ask. And other relations they will ask by giving t half at some time, and what is the t 90%. Okay, how much? At t 99.9%. Okay, so right, just substitute these percentages in the formula, you will get some relation between these two. If you are unable to get this, just look into the first video of this chemical kinetics discussion. Okay, and next one more thing you need to remember here, all radioactive reactions, what I am saying, all radioactive reactions are first order reactions. Okay, what I am saying, all these are first order reactions. Therefore, we can find the age of a particular wood or a particular sample or a particular thing like ancient things by using this first order reaction kinetics, like their ages we can find. Like for example, I am giving a wooden rod or wooden log I am giving you. So it belongs to some thousands of years back. So I want exact age of this particular wooden log. Okay, so we can find that using carbon dating method. What is that? Carbon dating method. Okay, that follows this first order reaction kinetics only. Okay, so now if I say, see, carbon log will be contains carbon atoms now. So in that we have some carbon 14. So carbon 14 is a radioactive isotope. What I am saying, it's a radioactive isotope, whereas carbon 12 is normally a normal non-radioactive species. Okay, so if it is a radioactive, so it will keep on disintegrating from all this many years. Okay, so now the concentration of C14 from the initial at the beginning to now, if we calculate, we'll get the time for that particular process. Okay, so now let us make one question on this. See, a wooden log having t half as 5000 years. What is the t half of this thing? 5000 years. Okay, and the activity or concentration of this radioactive disintegration of C14 is found to be 1/4 of its initial activity. Then find age of wooden log. Age of this wooden log. It's very simple. We can use our first order kinetics to solve this kind of questions. See, if there is any blur, please mention so that I will try to correct it all the time. Okay, see, find its age of wooden log they are saying now. So just what to take here, you can use first order kinetics here. See, time required for this process will be 1/k. See here, all k in this radioactive disintegration is taken as alpha. Alpha indicates radioactivity disintegration. Okay, disintegration constant. Okay, log here 2.303 log. So here you can take what is a C14 initial, like what we are writing, t equals to 1/k ln of a by a minus x now. So it is nothing but concentration initially, concentration after some time t right now. So I want the t here, so it means what is the concentration initially given? It is C14 you can consider. Now at present it is found that 1/4 of its initial activity. So you can write 1/4. So 1/4 of C14. This is C0. This is at some time t. This is becoming 1/4 of its initial. So you can remove these two values. Finally, we will be having 2.303, and lambda value we do not know, but its half life is given. What is the relation between half life and this constant here? See, constant and half life is having t T half is equals to 0.693 by K, right now. So here K is nothing but our lambda here in this case. So that is can be taken as K is equals to 0.693 by 5000 years. Okay, 5000 years. So you can write here 0.693. Here in the numerator you write 5000 into log 1 by 4 is there, means 4 by 1 we can write here. Okay, that's it. We are almost done with this. So time required, or what is the age of this particular species? See, log 4 I can write 2 log 2 right now. So 2 log 2 we can write. So that is 2.303 into log 2 by 0.693 I have. 0.693 and log 2.3 is the same value they are. So therefore you will get time for the age of this wooden log will be 10,000 years. How many years? It belongs to 10,000 years long ago. Okay, hope this type of calculation is clear. Okay, so this is one of the important method of calculation for the ages of wooden log or any other bone ages like dead bodies bone age. So like that we can calculate using this carbon dating method. Hope the discussion is clear on this particular thing, first order kinetics. Okay, and when it comes to second order kinetics, see, we will be having rate of a reaction. For example, reactant A is forming some products, okay, having initial concentration A here 0, and this is A minus X, this is X we are writing now. If this follows second order kinetics, how the equation can be written? So rate will be equals to K into concentration of A power 2 you have to write. Okay, it means rate increases 4 times if we increase the concentration of A 2 times. Okay, rate increases 4 times when you increase the concentration of A 2 times. If you increase the concentration of A 3 times, then rate becomes 9 times. Okay, why? Because 2 power 2 is 4, 3 power 2 is 9, like that. If you increase the concentration of A 4 times, then rate increases 16 times. Okay, because 4 power 2 is 16, that's what. Okay, by looking at this relation, we can able to find sometime if the given data contains this type of scenarios, then looking at the scenario we can find which order the reaction given is. Okay, right. And the next one here is, upon integration of this particular equation, like minus dA by dt is equals to K concentration of A to the power 2 we have now. Upon integration of this equation, you will get T is equals to 1 by K2 into 1 by A minus X minus 1 by A. This will be the integral equation for the second order reaction. For any nth order reaction, you will get time integral equation as T is equals to 1 by, see, second order it is 1 here, for third order it will be 2, for nth order it will be n minus 1 Kn into 1 by A minus X to the power n minus 1 minus A power n minus 1 will be the generalized nth order integral equation, you can remember. Okay, and what is the T half of this second order reaction? So it's very simple. So T half means the concentration becomes A minus X becomes half of its initial concentration. You can just write A by 2 here, that is A here, 2 here, 1 by A, that's it. So T half will be now equals to K 1 by K2A, that's it. This is the T half of second order reaction. Now how they related? T half is inversely proportional to the initial concentration of reaction, whereas zero order is directly proportional. First order is independent, second order is inversely proportional, and third order will be also be inversely proportional with a square. Okay, okay. So for third order you will get T half is equals to 1 by, T half is inversely proportional 1 by K3, A cube will be there. Okay, for A square will be there for third order. So for any nth order, from second to any nth order, not first and zero order, so it will be T half is inversely proportional to Kn A to the power n minus 1 will be seen. This is a scenario. okay, for any nth order. Oh, voice is not coming up. Sorry. Now once again look at here. I just wanted to repeat it. See, what are the factors affecting rate of a chemical reaction? First one is concentration. If concentration of reactant decreases, rate also decreases from first order to nth order. Okay, but zero order is independent of initial concentration of reactant. Okay, now temperature. So temperature, as temperature increases, rate of reaction also increases. I hope it's clear now without having any disturbance in the voice. So now what I am saying, rate of reaction increases with increase in temperature. So this is a relation, like temperature goes on, as temperature increases, rate of reaction also increases. This is a curve we have, and it is observed that practically the rate of a reaction increases 2 to 3 times for every 10 degrees rise in temperature. Okay, so it will be 2 to 3 times for every 10 degrees rise. If I increase temperature from 30 to 40, rate becomes double. If it is R, becomes 2R. Okay, it will be faster now. Okay, now how can we say how many times rate increased when temperature rises from 30 degrees to 80 degrees? I am asking. Simply you write 30 to 40, 40 to 50, 50 to 60, 70, 80, you write like that. So it is R at 30 degrees, becomes 2R at 40, 4R at 50, again multiply with 2, that is 8R at 60, 16R at 70, and 32R finally at 80 degrees. Okay, this is a one way of doing the question. Okay, this is 32, answer is perfect. Next, same question we can solve in this manner. Rate, final rate RF is equals to mu to the power delta T by 10 into Ri. It means this is a final temperature. What is the final temperature? 80. So rate at 80 degrees Celsius will be equals to mu. What do we mean by mu here? Temperature coefficient. So what is the temperature coefficient mentioned here? So if nothing is mentioned about temperature coefficient, just take the minimum number 2. Okay, so 2, if not mentioned in the question, take 2. And what is change in temperature? Change in temperature 80 minus 30, 50 you take, and here it is 10. Okay, that's it, into initial temperature R at 30 degrees Celsius, that's it. So you will get final temperature, final rate is equals to 32 times of initial rate. Okay, that's it, this will be the scenario. Now tell me, what is the answer for a reaction? For a reaction, rate increases 3 times for every 10 degrees Celsius. Then what will be the rate? What will be the rate at 90 degrees Celsius? 90 degrees Celsius, if rate at 30 degrees Celsius is X. So very easy. So what is our temperature coefficient mentioned here? 3. So I want how many times, or what is the rate of reaction at 90 degrees for this particular question. Use this formula, easily you can answer. Okay, and mention your answer in the chat box for this particular question. Okay, so this is a homework question based on the previous discussion. Right, next, now here we have seen only effect of temperature, means for every 10 degrees Celsius we discussed that rate increases 2 times, 3 times we discussed. Now the exact effect of temperature and rate of a reaction is given by Arrhenius equation. Arrhenius equation says us the exact effect of the exact effect or relation of temperature on rate of reaction, exact effect of temperature on rate of a reaction. Okay, so what is the Arrhenius equation? Here we have K is equals to A e to the power minus EA by RT. What is K here? It's a rate constant. Say rate constant. So greater the rate constant, greater is the rate of a particular reaction. So now how this rate constant varies with temperature, just now we discussed. So Kt will be having like exponential relation. Okay, so as temperature increases, K also increases. Now from this equation, let us draw or let us conclude how can we relate a rate constant again, especially at two different temperatures from this particular equation. Very simple. So send this A this side. So here A is called Arrhenius parameter. Okay, for a first order reaction, so it will be also called as like the pre-exponential factor also called as frequency factor here. Okay, because its units are second inverse now in case of first order reaction, because rate and this rate constant and this A will be having same units, therefore I am calling it as frequency factor in case of first order reactions, because second inverse will be the units for that A in first order reaction. Okay, and now here EA means activation energy, temperature here. Okay, R is constant. Okay, so K by A will be equals to e to the power minus EA by RT. Okay, you send this E here, becomes ln of K by A equals to minus EA by RT. So from this you can write ln of K is equals to minus EA by R into 1 by T plus ln A. Okay, so from this you can draw the graph. From this you can draw the graph for rate constant ln K versus 1 by T temperature. Okay, slope is negative, intercept positive, so you will get like this, and slope can be now minus EA by R, and intercept is how much? This is ln of A. Okay. Okay, so if I write in terms of logarithms, log K will be equals to minus EA by 2.303 or 1 by T plus log A. So in this case again slope changes, the value of slope changes, log K by 1 by T, now slope will be minus EA by 2.303 R. Okay, right. So they will ask what is the slope for this reaction, for this particular equation that comes from Arrhenius equation. Okay, then next at two different temperatures, how this rate and temperature related. So just take one equation as log K is equals to EA by 2.303 at temperature T1, you take K1 and this is T1 plus log A, and at temperature T2 consider rate constant as K2, because value of rate constant changes with change in temperature right now. So that's why K1, K2 are different values here, depends on the temperatures. T2 plus log A. Okay, so now you can take from these two equations, you can get log K2 by K1 is equals to EA by 2.303 or 1 by T1 minus 1 by T2. Okay, this is what we will get. Okay, so here EA indicates activation energy and denominator 2.303 R. So at higher temperatures, see T2 is a temperature having rate constants K2 and K1 is a rate constant at temperature T2. Okay, so as temperature increases, rate of reaction also increases. Okay, remember this. Okay, and questions related to this will be doing in the next session, that you can use R equals to 8.314 joule Kelvin inverse mole inverse, and or R you can use 2 calorie per Kelvin per mole. Okay, I will give one question as a homework, you just try this. If not, we will be discussing them in the next session. Okay, so I am saying at temperature 200 will take 200 degrees Celsius, K1 is equals to x, okay, K1 is equals to x, and at 400 degrees Celsius K2 is equals to again this is 2x, let us say, okay. So this is 2x, then tell me activation energy for this particular reaction, what is EA in terms of calorie per Kelvin per mole, per Kelvin units, okay. I want calories per Kelvin per mole. You can use this R value as 2 calorie per Kelvin per mole. So this is the data I have mentioned. I want answer of activation energy in calories, okay. Use the data given here and just mention your answer in the chat box, okay. And we will solve this kind of questions in the next session, that is tomorrow's session, on this remaining part of this chemical kinetics with the PYQs related to this discussion, okay, right. So I hope you have watched complete session on this chemical kinetics, and if you have any confusion, just mention in the chat box. We will discuss them in the upcoming session. Thank you.